Good morning to everyone present here. Design of pre-stressed concrete element. The subject code 17CV82. Module 1 Introduction and Analysis of Members. In that session 4, the course outcome is analysis the stresses encountered in PSC elements during transfer and at working. Presented by myself, Naveen G.M. A beam of I section spanning 12 meter has a flange width of 300 mm and thickness of web is 80 mm with an overall depth of 800 mm. The parabolic cable has E is equal to 300 mm at center and E is equal to 0 at ends. It carries an initial pre-stressing force of 150 kN. The live load of the beam is 3.5 kN per meter. Assume a loss of 20%. Calculate stresses at mid-span session during the transfers of pre-stress during working load condition. In that, what is the given? That is 12 meter span, and also overall depth of the beam is 800 mm and width is 300 mm, and also eccentricity of 300 mm from the bottom. It carries a pre-stressing load of 150 kN pre-stressing force here at 150 mm center from the bottom, and also here UDL of 3.5 kN per meter. It carries a UDL. Solution. Here cross section of the section A is equal to 2 times of, you see this one, 300 into 80, here 300 into 80, that is 2 times. Then 80 into 640, that is 80 into 640 gives area of cross section 9.992 into 10 raised to 4 mm square. Assuming density of concrete is equal to 25 kN per meter cube here, the self weight of the section is equal to, that is 9.992 into 10 raised to 4 divided by 1000 into 1000 into 25,000 is equal to 2480 Newton per meter. This is converted for meter. Okay. Then girder moment MD at the central section is equal to 2480 into 10 raised to 12 square divided by 8 into 1000, that is 4.464 into 10 raised to 7 Newton mm. This is the girder moment, that is due to dead load. Then superimposed load is equal to 3.5 kN per meter. Then bending moment due to superimposed load ML is equal to 3.5 into 10 raised to 3 into 12 square divided by 8 into 1000, that gives 6.3 into 10 raised to 7 Newton mm square. The total moment MT at the central section, that is 4.467 into 10 raised to 7, this one, plus 6.3 into 10 raised to 7 equal to 10.94 into 10 raised to 7 Newton mm square. Then the moment of inertia about neutral axis of bending is equal to BD cube by 12 minus BD cube by 12. This is big BD cube by 12. This is minus BD cube by 12. Here moment of inertia is taken as, that is big body cube minus body cube by 12 means this is big B is equal to 300, big D is equal to 800. Okay, here small b is equal to taken as 300 minus 80. Okay, that is 220. Here 800 minus 160, that is 640 is the small d is taken. Then coming to the calculation of this I value. Then here big body cube by 12, that is 300 into 800 cube divided by 12 minus 220 into 10 raised 640 cube divided by 12, that is 7.994 into 10 raised to 9 mm to the power of 4. Hence P naught is equal to 150 kilonewton is given here, 150 kilonewton, and also loss of stress is equal to 20% is given here. Therefore loss ratio nu is equal to 0.8 is given. Therefore 1 minus 0.2 gives 0.8. Nu is equal to 0.8, that is 80%. Therefore effective pre-stressing force P is equal to nu P naught. What is P is equal to 0.8 into 1.5 into 10 raised to 5 gives P is equal to 1.2 into 10 raised to 5 Newton. Okay, this is the net P value, that is pre-stress force available in a member. Here note 192 is there. Why note 19, what is note 2 says means maximum extreme fiber stress refers to extreme stress at session where bending moment is maximum. Okay, the maximum bending moment refers to the extreme fiber stress at the session where bending moment is maximum. Then note number 2, that is there is need to evaluate maximum bending moment stress at mid session MD, that is moment due to dead load, moment due to live load, that is total moment MT, and E are the corresponding to mid section where bending moment is maximum. Then to find extreme fiber stress at transverse of pre-stress, let us Fu1 and Fu2 correspondence result in extreme fiber stress in concrete at top and bottommost fiber at center section respectively. In that the top fiber stress and bottom fiber stress is calculated here. In that Fu1 is equal to, that is P naught by A plus P naught E Y1 divided by I plus MD Y1 divided by I. Here P naught is the initial pre-stressing force and A is the area of cross section and E is the eccentricity, Y1 is the distance from top, and also I is the moment of inertia, MD is the moment due to dead load at transverse load. Here Fu1 is calculated by substituting P naught value equal to 1.5 to 10 raised to 5, A is equal to 9.92 into 10 raised to 4, and P naught is equal to here 1.5 to 10 raised to 5 into E is equal to minus 300, and Y1 is equal to 400. Here Y1 is plus, why? Because at the top fiber this is plus not minus. Then I is equal to 7.9941 into 10 raised to 9 plus 4.464 into 10 raised to 7, that is MD value, into Y1 is 400, that is 7.994 into 10 raised to 9 is the I value. Here we substituting this value and solving this equation, we are getting Fu1 is equal to 1.494 Newton per mm square. That is positive sign indicate the compressive stress at the top fiber stress. The bottom fiber stress Fu2 is equal to P naught by A plus P naught E by 2 divided by I plus MD by 2 divided by I. That is equal to 1.5 into 10 raised to 5, that is P naught, divided by 9.992 into 10 raised to 4, that is A, plus P naught is equal to 1.5 into 10 raised to 5 into minus 300, that is E value, into Y2 is minus 400, that is represent the bottom distance, in 7.9941 into 10 raised to 9. Then plus 4.464 into 10 raised to 7 into minus 400 divided by 7.994 into 10 raised to 9. That gives the value 1.53 Newton per mm square for a bottom fiber stress. Then positive sign indicate again compressive stress at bottom fiber stress. Then this is the resultant stress diagram, that is stress diagram for various sections due to pure axial, due to eccentricity and due to load moment. We are getting this stresses diagram. In that we are finally getting a resultant fiber. Then P naught A, this is P naught A at top and bottom. P naught E by 1 divided by I, this is negative, that is why, because E is the negative here. Then P naught E Y2 divided by I, here E is equal to minus, Y2 is equal to minus into minus gives plus value. Then MD Y1 divided by I, that is MD is equal to moment due to dead load. Y1 is the distance from top fiber. This is both are positive, therefore positive. Here MD positive, MY is the negative value, therefore we are getting negative at the bottom. Then this combination, this positive, negative, then positive gives Fu1 value, how much we are getting here, 1.494. Then Y2 value is equal to bottom. What is that value? That is 1.53 Newton per mm square. This value is the FL2. Here FL1 is this one. Then to evaluate extreme fiber stress at working load condition, this is the second condition. We calculate let FL1 and FL2 respectively. Resultant fiber stress at top and bottom. Most fiber at center section. Then the top fiber stress FL1 is equal to P by A plus PE Y1 divided by I plus MT Y1 divided by I equal to P is equal to how much? That is after the losses 1.2 into 10 raised to 5. This is P naught A. Then A is equal to 9.992 into 10 raised to 4 plus E is equal to P is equal to 1.2 into 10 raised to 5. E is equal to minus 300. Y1 is equal to minus 400. I is equal to 7.9941 into 10 raised to 9 plus 4.464 into 10 raised to 7 into, that is 400 divided by 4.994 into 10 raised to 9. This solving of this equation, we are getting 4.873 Newton per mm square. That is positive sign. That is positive sign indicate the compression here. Okay. Then coming to the bottom fiber stress, that is FL2 is equal to P by A plus PE by 2 divided by I. plus mt by 2 divided by I. That is, P is the pre-stress force available, E is the eccentricity. Then here P is equal to 1.2 into 10 raised to 5 by 9.992 into 10 raised to 4 plus 1.2 into 10 raised to 5 into minus 300 into minus 400 divided by 7.9941 into 10 raised to 9. This is the moment of inertia value. Here observing y2 is the negative for minus 400. Then 4.464 into 10 raised to 7, that is empty, minus 400. Then I is equal to 7.994 into 10 raised to 9. Then FL2 is equal to minus 2.473 Newton per m square. This is negative. This negative sign indicates the tensile stress at the bottom. Okay. Then coming to the stress diagram, here P by A is 1.2, here P by A is 1.2, then here P E y1 divided by I, that is negative, P E y2 divided by I, that is positive. Here MD y1 divided by I positive, that is gives 5.473. Then MD y2 divided by I, that is 5.473, that is negative. The total 1 plus 1.2 minus 1.804, 5.474, that gives 4.873. Then 1.2 plus 1.801 positive, negative is 5.473, that is 2.473. It gives negative. This is due to axial force, this is due to eccentric, due to here the total movement, and this is due to resultant stresses developed in a membrane. This is the stress diagram. This indicates the this side negative, this side positive. You see the line of action. This is the positive side, this is the negative side. This is negative, this is positive. Observe this point. This is the negative and this is positive side. Okay. Then coming to the next one, that is the mid span section of a simply supported girder of span 6 meter is a symmetrical I section 200 into 400 mm. The flanges are 80 mm thick, web is 60 mm thick. The girder carries 2-point load of 25 kN applied at 1/3 span point. Determine initial pre-stressing force and its eccentricity so that tension in concrete will be limited to 1 Newton per mm square and 0.5 Newton per mm square transfers at service load respectively. Loss ratio is equal to 80%, concrete weight 25 kN per meter cube. This is the symmetrical I section. In that, width of the I section is 200 mm. This overall depth 400 mm is given. A span of 6 meter. You observe this 6 meter, and also 2-point load of 25 kN. You take that 25 kN at the point load, 2-point load. Due to this point load, the cable is under the trapezoidal in shape. Then y1 is equal to this positive, y2 is equal to negative 200, 200. Overall depth 400, y1 plus 200, y2 minus 200. Then that to determine the initial force, that is P naught and its eccentricity E. Therefore, we find out the P naught and E value, and also tension in a concrete will be limited to 1 Newton per mm square and 0.5 Newton per mm square at transverse and at service load respectively. Okay, at the transverse and service load tension ಎಲ್ಲಿರುತ್ತೆ ಅದನ್ನು ಲಿಮಿಟ್ ಮಾಡಿದ್ದಾರೆ 1 Newton per mm square and 0.5 Newton per mm square. Then solution of this problem: the cross-sectional area of the beam A is equal to 200 into 80 into 2. What is this 2? That is symmetrical I section. In previous problem also we discussed here 200 into 80, 200 into 80. This is 60 into 240. That gives A value 4.64 into 10 raised to 4 mm square. Then self weight of the section is equal to 4.64 into 10 raised to 4 into 25,000 divided by 1000 square is equal to 1160 Newton meter. Then girder moment MD is equal to WL square by 8 into 1000, that is 1160 into 6 square divided by 8 into 1000. That is MD is equal to, MD is equal to moment due to dead load, that is uniformly distributed load. Due to that 5.22 into 10 raised to 6 Newton mm we are getting the moment due to dead load. Then 2 point loads of equal magnitude which are equal space from the support is given by, that is total moment, that is due to live load 25 into 2, that is 25 kilonewton, that is 25 into 10 raised to 3 into 2 into 1000 per Newton per mm square convert ಮಾಡಿ is equal to 50 into 10 raised to 6 Newton per mm square. Then total moment MT is equal to, that is MD plus ML equal to 55.22 into 10 raised to 6 Newton per mm square, that is 55.22 comes the value total moment. Here Y1 is equal to 200 mm square, Y2 is equal to minus 200 mm square. We already discussed in that diagram also. This is negative Y because bottom. MT, MI, that is moment of inertia about neutral axis of bending, I is equal to BD cube by 12 minus small bd cube by 12. Why? Because this is symmetrical I section. Big BD and big beam is 200, big D is equal to 400. Okay, small b is equal to that one 200 minus 60, that is 140, that is 400 minus 120, that is 280 small d. It is 200 into 400 cube divided by 12. This is 140 into 240 cube divided by 12. That gives I value 9.054 into 10 raised to 8 mm to the power 4. Here loss ratio is equal to nu is equal to 0.8. That is given here in your problem. At transverse of stress, let Fu1 in the stress developed in concrete at transverse of stress as far as tensile stress is concerned, that is at the transverse load condition we are given the value -1, the tension at the top fiber. Therefore Fu1 is equal to P naught A plus P naught E Y1 divided by I plus MT Y1 divided by I, that is for top fiber stress. For known values only, sign conversion must be adopted depending upon the sign logic is adjusted at the latest state. Okay, that is Fu1 is equal to -1. Tension is negative, we are taken, equal to P naught divided by 4.64 into 10 raised to 4 plus P naught E 200 divided by 9.05 into 10 raised to 8 plus here 55.22 into 10 raised to 6 into 200 divided by 9.05 into 10 raised to 8. This lead, this 55.22 into 10 raised to 6 into 200 divided by 9.05 into 10 raised to 8 gives how much that value? 12.02. Okay, this is 12.02 is the value of this one. Then 200 divided by 9.05 into 10 raised to 8 gives 2.22 into 10 raised to 9 into 10 raised to 7. Then here P naught, that is 4.64. This is the value. This is P. This P naught is replaced by P into nu. Here P into nu. P naught is replaced by nu into P. Here P is equal to P naught is into 2.2155 into 10 raised to 4 minus 4 plus P naught E into 2.20709 into 10 raised to minus 7 is equal to minus 13.203. This is the adding up this value gives minus 13.203. This is taken as equation number 1. Then at working load condition, here you see this one, at transverse load condition top fiber stress we are taken, but at working load condition at the bottom we are getting a tensile stress. Let FL2 is equal to P by A plus PE by 2 divided by I plus MT by 2 divided by I. Then FL2 is equal to nu P naught by A plus nu P naught E by 2 divided by I plus MT by 2 divided by I at the bottom. Here nu P naught is equal to P here. P is replaced by nu P naught, that is initial pre-stressing force. Here nu is equal to P naught by 2 E by I plus MT is the total load by 2 divided by I here. Then we substitute the respective value, that is minus 0.5 is given in your problem, equal to 0.8 into P naught by 4.64 into 10 raised to 4 plus 0.8 into P naught E into minus 200, that is eccentricity, that is Y2 is the minus 200 by I value 9.05 into 10 raised to 8 plus 55.22 into 10 raised to 6, this is MT total load, minus 200 is the Y2 value, this is I value 9.05 into 10 raised to 8. So substituting this value, we get this equation minus 0.5 of P naught 1.7241 into 10 raised to minus 5, this 0.8 divided by this value. Then 0.5 into minus 200 divided by 9.05 gives 17.64 into 10 raised to minus 7 of P naught into Y E minus 12.203. Then this equation gives P naught into 1.724 into 10 raised to minus 5 minus 17.676 into 10 raised to 7 P naught E equal to 11.703. That gives, this is equation number 2. To solving this equation 2 and 1, here this is 1, this is equation number 2, by simultaneous equation 1 and 2 solving, P naught is equal to 2869451.115, we are getting this value. Then P naught E is equal to minus 37970824.31, we are getting this value. We substitute this 2 value in this equation. Okay, we are substituting P naught value in this equation. We are getting E value equal to minus 131.1821. This E value eccentricity. We are getting this value. This is P naught, P naught E and P value. By solving this equation and this equation. These are the some references we are refer for preparing this session. Some textbooks and also some code books we are using for preparing this session. Thank you for listening this session. If any queries, please ask me. If any query, please ask me here.